Very good morning for all of you. Let us try to discuss the landmark experiments or maybe the concepts which were prescribed in your syllabus. Yesterday, we discussed on the cooling of atoms by the mechanism of laser. This laser cooling of atoms is also created a great anxiety and anxiety among the scientific community and in the 20th century, that is between 1901 to about 2000, and made it as a landmark. What happened actually, I'll go through the text, don't explain in between steps. During 1970s and 80s, means between 1970 to about almost 1990, you can call, researchers developed the techniques for cooling of an atoms to very low temperatures using laser light. Yesterday, I was discussing in such a way that as you are going decreasing the temperature or as you are going reducing the temperature of a system, for example, what will happen actually? Being at about some 25 to 30 degree Celsius at room temperature, the molecules or the atoms, of course, you can't get them as the individual isolated atoms actually, unless you create a pressure which is quite low. It moves with the speed of almost about 4,000 kilometers per hour or about some 1,000 kilometer per 1,000 kilometer per second of that kind actually. Means to say about one kilometer, not 1,000 kilometer, about 1 kilometer per second of that kind actually. If they move with such a high speed, it is difficult for us to monitor, it's difficult for us to study or understand the phenomena of it. What one has to go, let us try to reduce the temperature in such a way that how they will. Even if you reduce the temperature to the extent of about minus 273 degrees Celsius or to the extent of about a fraction of 0 Kelvin, right? It's about less than 1 degree Kelvin if you expect actually, still it is difficult. Means they thought in scientific community at that time, almost about 50 years back, they thought that in such a way that if we cool the atoms, particularly to a very low temperatures, and even with reduction in the pressure, actually, how they behave, one can able to see. Earlier observations for ions they studied, because being an ions, you can bring them the ions into in an isolated way, means in a stable way, isolated way, then you can make use it for the studies. Because one more disadvantage of conducting the experiment when Einstein and others were there with optics was that there was no invention in this, there was no availability of the laser. They had a weak source like an sodium lamp, vapor lamp, or maybe a mercury lamp of either vapor or whichever you can call. Whatever you are conducting the experiments in your regular labs, either sodium lamp and vapor lamp, they are the one which used to give the energy or source of the energy for the conduct of the experiments, particularly in optical regime. But later, with the invention of the laser or discovery of the laser from 1960 onwards, actually, the entire optics has changed this scenario and experiments were strengthened to study in detail because of the great advantage of the lasers as a collinear, highly intense, monochromatic, so highly monochromatic actually. There is no much deviation with the half width at full maximum at that extent. In 1970s and 80s, they tried to develop some techniques for cooling. Means either you can freeze them or you can remove some of the energy by some technique, or maybe you can take away the heat content from that system and or allow the atoms, any kind of an atoms actually, to a region where the temperature was quite low. How they achieve? They achieved with the technique of using the laser light. The work which was led to the improvements, particularly of this cooling atoms in atomic clocks and observation of new ultra cold state of the matter. New ultra cold means it is not the cold at all, it is ultra cold. They can go to the extent of several micro Kelvin, micro degree Kelvin, actually, micro degree Kelvin of that kind. Physicists learned particularly how to use lasers to cool atoms to the temperatures just barely above absolute zero. Means I told that between 0 to 1 degree Kelvin need not be even to the extent of milli degree Kelvin or milli or even micro Kelvin to that extent. During 1978, researchers cooled ions to somewhat about 40 Kelvin. 10 years later, about 70, 88, you can expect neutral atoms had gotten a million times colder. about 43 million Kelvin. 25 to 43 million Kelvin, there were, sorry, 25 to 43 microkelvin, there were several experiments which were conducted on that at least. But the basic principle remained the same. Either you go with the microkelvin temperature or you want to the extent of degree Kelvin or at room temperature. The principle lies the same thing. That is basic physics principle. Of course, this is the principle from physics background only, or the concepts utilized in physics was became the basic principle. It remains same. What it made? Use the force of light, or you allow the light to pass through on an atoms or maybe a group of atoms or a cloud of atoms to slow them down. If you are giving an energy, always there are quite good comfortable. Wait, maybe if you are highly energetic, you will not sit at one place. You will not yeah, work at one place. You will not stay at one place. You will not stay for quite longer duration because of the energy. It's not the momentum. Means either enthusiasm, curiosity, everything makes us in such a way that nobody can stand at a particular place. Nobody can sit at a particular place for quite longer duration. Actually, the same thing will happen for the objects without life. If they possess the kinetic energy, because of the kinetic energy, they have to move from one place to another. Maybe for macroscopic things, you can observe the displacement of an object or maybe movement of an object because of their momentum and also the kinetic energy. But for at micro level or even atomic level or even subatomic level, we may not found through the visible. There are several devices, there are several techniques to estimate that the motion or the movement of the either atoms or maybe subatomic particles or even photons from one point to another point. What happened? The force, if you allow the laser light or any kind of a beam, if you apply it directly to the atoms and you bring them their speed, you reduce their kinetic energy, you reduce their momentum. If we reduce the either kinetic or energy or the momentum, certainly the slowed down atoms will remain stationary for a appreciable time of the order of about zero point 0.1 seconds or maybe one tenth of a second of that kind. This work led to the creation of a new quantum form of matter called the Bose-Einstein condensation or condensate they can call. And the modern atomic clocks and as well works on this principle, and it fetched minimum at least two Nobel Prizes there. 19 sorry almost 2001, almost 2001 actually. Still that is the 20th century they can call actually. Means to say the original reason to cool the atoms with a reduced speed of their motion was allow more precise measurement of the atomic spectra and later to improve the atomic clock to that extent. From 70s, now 2023, if we expect, the atomic clocks are functioning. Even there is no change in the time of the order of about 10 to the power of minus 14 of a second, they can call. Otherwise, getting the precision on your mobile for GPS or maybe tuning the satellites space to work to the better extent may be a difficult task. In 1970, that is the same case what you expect in the mid of almost later part of the 70th century. Dave Wendland and his colleagues, he's a gentleman actually, worked at NIST. Remember this NIST actually is the National Institute of Standards for Under Technology in Colorado, USA. Followed theoretical proposals or accepted the proposals from the theoreticians and managed to go for cooling the atoms, particularly magnesium ions, by making use of the laser as a technology. This I will explain. This I will explain right now here. Okay. It looks like the text doesn't matter. Dave Inline and his colleagues confined the ions electromagnetic trap. How you do that? You take the isolated ions actually. This is difficult for the make them isolated atoms to a great extent. If you bring the ions in an isolated way, in an electromagnetic trap, apply the electric and magnetic field together, a particular perpendicular to each other, and hit them with the laser or allow the laser beam to fall on that, the gas of ions or confined ions, which are tuned to a frequency just below the resonance frequency for the ion. Why? Because if they vibrate, if they oscillate with the resonance, that is the vibration, vibration of the ions, or maybe the transition of the ions they can call actually, with the electric and magnetic field, if it vibrate, what happens? Because of the absorption of the energy from the photons, which are emitted by the laser source, gives us a little bit more energy, and they may go with excited, and because of that excitation, the kinetic energy becomes quite larger. It may not be trapped. It may not be trapped. At rest, means maybe for a momentary rest, I can call, the ions absorb the photons, no doubt, at the resonance frequency. But if they are moving towards the beam, for example, laser source, assume that if the ions, any kind of an ions, the positive ion or negative ion, moving towards the beam, that is the source of light, its lower frequency appears Doppler shifted. Doppler is a great scientist. Because of the Doppler shift, you can see that if the any of the targets are moving towards the source, their frequency enhances, means energy enhances, or wavelength decreases, shift in the frequency or shift in the wavelength. If they move apart, if they are separated, if they are moving away, the frequency drops or wavelength increases. It shows that red shift and blue shift is very well known for you. I don't want to touch upon that actually. After shifted to the correct frequency, which allowing them absorb the photons coming towards them. These photons, that is the photons which are coming from the source, slow down the ions until the cooling effect is balanced by the small, that is always when the laser is on. Is if you are allowing the laser beam to pass through, certainly it should go for heating effect. Fine. This collimated beam of the electromagnetic radiation at a particular point, at a particular force, enhances the energy. Thereby, it causes means it makes the rise in the temperature or heat content or delivery of the heat content. But what happens if because of these things, because of the Doppler shift, both are approaching each other, the electromagnetic photon hits electromagnetic photon, that is the laser beam photons from the laser hits the incoming ions, and thereby reducing the energy of the ions. If they reduce the energy of the ions get slowed down. This ion gets slowed down means because of the slowdown, temperature comes down. We are taking them to the cooler phenomena. Later years, about after 10 years of that time, this heating which comes from the atoms by recoiling every time, maybe in the random direction earlier, or maybe absorb a photon in any particular direction, would ultimately limits the cooling possibility to that what is as Doppler cooling. They also adopted a technique called the Doppler cooling technique. This idea of cooling of the ions made them earlier in the 80s, 70s to 80s, there was a well-known technique for this. It's well-known this is they worked on that. There were several experiments. There were several campaigns which were going on across the world actually. This idea of cooling of ions made them to think whom is those two scientists, what I told actually both. Okay, think of the possibility to do the same thing with the neutral atoms. See, that's the beauty. Actually. Why we are doing actually, if you are having an idea of doing an experiment at one part, you can expand that idea to the other field, maybe from condensed matter physics to the nuclear physics to a spectroscopy to the rest of them. Or if you are conducting an experiment with iron, you can also conduct an experiment with the cobalt, nickel, or maybe gaseous metal of that kind. This is how it can go. But thing is that there should be a logic doing that actually. It can't be extended for all actually. You can't ask the elephant to climb a tree rather than that spiral or some other things which are doing it. Okay, after 10 years, means around that 1982, Phillips and the Metcalf, they published the first paper, of course, published the first paper in the sense, even though there is a first paper from them, in this field, first paper they are calling on laser cooling of the neutral atoms. Means they worked. They thought of, instead of ions, they thought of why can't we do the experiment on the atoms? Preferably, they will go with the neutral atoms. If not, of course, why neutral? Because if it is excited or ionized, they can call them as the ions. They conducted the experiments on neutral atoms. They sent a beam of sodium atoms through a magnetic field. Means there was a magnetic field. Okay, within the magnetic field, they sent a sodium beam or beam of ions, not ions actually, sodium, neutral sodium atoms actually, a gaseous material that was large at the entrance to the upper base, but became gradually smaller over a distance of about 60 centimeter. It is like a pipe, they can call cylindrical pipe. If you apply the electric field, magnetic field, allow them the gaseous molecules to pass through. While moving through the field, The atoms headed directly into an off-resonance laser, yes, that used the Doppler cooling to reduce the range of atomic velocities among the atoms in the beam. What happened? The laser also slowed down the beam as a whole. During deceleration, or with the reduction in the energy, with changing in the magnetic field, changed the atom's resonant frequency. So that slowing down and cooling continued over a long distance, what we can call a centimeter, allowing them to reach about 40% initial velocity. Means whichever may be the value they can expect with that availability of the technology and the techniques, actually, they slowed down the incoming atoms, neutral atoms, with a speed of almost 40% in drop. Means thereby efficiency enhanced for them to study the concept of what we can call concept of several properties actually with the reduction velocity. Now, this effect is known as the Zeeman's law. Zeeman's law here. Zeeman's law here. One Zeeman's law here. This is Zeeman's law here are known as a standard device for decelerating of atom beam. If you send any kind of an atomic beam that can be used, Zeeman's law device can be used to reduce the speed of atoms. But thing is that it should be at magnetic field. It should be in a magnetic field, and the temperature should go almost of that of 270 degrees Celsius, Kelvin Celsius, or about 0 to 1 degree Kelvin of that order. And the pressure should be very low. It should be of low density. You can't expect the experiment to be performed in our normal temperature. Being this, what happened here? This took a generation. Laser cooling techniques, which were improved after 1960s, almost by 1980, there's no doubt in it. Researchers had achieved what they thought were with the lowest possible temperatures. Maybe according to the Doppler cooling theory, that theory helped us to work out to reach to the extent of minus 240 microkelvin for sodium atoms. Don't treat this as the hyphen actually. They minus 240 means almost about 270 means about 40 to 50 degree Kelvin of that kind. Okay. To minus 240 microkelvin actually it is minus 240 to Kelvin for the sodium atoms. In fact, in 1988, that was in 70s actually, Phillips team used three mutual perpendicular pairs of lasers. I will explain that actually. Means perpendicular and sorry, they are mutually against means take a two laser beam heading to each other, keep the atoms at the center. Instead of two, they have taken three mutual perpendicular pairs, they can call. This is six laser beams to cool the sodium atoms with the laser frequencies somewhat different from other labs. Okay, this they achieved. They discovered using this theory several new temperature measurement techniques and that their atoms were at about 43 microkelvin. Remember, theories immediately means that is the theoreticians quickly explained the unexpected cooling mechanisms which were happened by including more atomic states and effects of laser polarization previously which was not known actually. Previous to that, cooling models were overlapping with simplicity actually. There was an overlapping earlier. Because of this 1988 onwards actually this team has worked a lot. By this, in later in 1988, the three scientists, this is the Claude Cohon-Tandadozzi of the Superway in Paris, and his colleagues broke the recoil limit. That is another assumed lower limit on cooling actually. Recoil limit I explained very earlier when Wu et al. Have done some experiments with the nuclear resonance, nuclear magnetic resonance, NMR of that kind actually. They broke from that to this, actually still they took the atoms to a lower temperature. It was guided by better theories later after 1888, such as improved understanding of Doppler cooling. Experimentalists performed several experiments where they can be reached much colder temperature and developing an additional cooling techniques. Therefore, Phillips, along with the followed by this Doppler cooling, this is a sub-Doppler cooling they can call. Sub means still further sub. cooling of methods from the Doppler technique was an early step in 1995, means 1988 to 1995, remember, after some few years of the gap, creation of Bose-Einstein condensate. Bose-Einstein condensate. It is a new state of the matter where gaseous atoms all drop to the lowest possible energy. So, if you go on decreasing the temperature, if you reach zero, exactly at the zero, maybe small values of the order of microkelvin, atoms will be staying at atoms will be sleeping, they can call. It will not have, they will not possess any energy. They apparently will be at some place. This Bose-Einstein condensate is a new phenomena. It is a new state of matter. It is the fifth state of matter. I will explain or show. This concept is used in atomic clocks, and these atomic clocks are benefited well, and they reached a greater extent to the extent of necklaces. They reach it to the extent of okay. They reach it to the extent of one. They reach it to the extent of they reach it to the extent of reaching micro kelvins to a great extent. The latest generation uses techniques which derived directly from what Phillips and his group did in 1980s. Three scientists, Phillips, Chu, and Cohen Tandojo, won the Nobel Prize. Yes, of course, that work won the Nobel Prize in 1997 for developing laser cooling. Another prize, 2001, which was awarded for the creation of Bose-Einstein condensates. This Bose-Einstein condensates also I will explain. I will take not much more than that. After completion of what happened? This is the last slide against for the description. The work of the Chu, then Claude Cohen, and the Phillips. This you can call them as the et al. To a greater extent in the field of laser cooling and the trapping as breakthrough in the theory and experiment within the field of lower temperature and has led to a deeper understanding of interaction between light and it has also led to an intense worldwide activity within the atomic or molecular and optical physics. Together, AMOP, what you can call, we will join different electives in the next semester with this community and has opened up new roads, new avenues, new paths towards this quantum behavior of dilute atomic vapors at very low temperature. Here, in this context, dilute in the sense the density is less, it is highly open. This is low pressure low pressure sample or the pressure was very low and dilute. These techniques of laser cooling and trapping are used in fundamental high resolution spectroscopy and to study the ultra cold collisions. You can also call it as ultra cloud also. Cloud in the sense the number of molecules per unit volume should be very less. They find the applications in the construction of an atomic clocks, atomic interferometers, like Michelson interferometer you told me, similar to that, an atomic interferometer to study the interaction of the atoms, and atomic laser, atom lasers, of course, helium neon laser, here something semiconductor laser, and in the development of instruments for atomic optics and atomic lithography. Lithography is a kind of a tool used to record the phenomena recent applications, not now, at that time, around 90s, related to the 1997 Nobel Prize in Physics are the first observation of Bose-Einstein condensation, a dilute atomic gas, development of first rudimentary atomic laser. Earlier laser was something like that, different. It was a highly robust and very strong laser of that. John's yesterday I was explaining the same thing. In this regard, John Kepler, in an attempt to explain why the tail of a comet entering our solar system, of course, it enters everywhere. We observe for our solar system, always points away from the sun. He suggested in 1916, assume that even though theory we are saying the 20th century and Nobel Prizes, suggested in 1619 itself that light can have a mechanical effect. See, if you put a hand on the table, or maybe wherever you are sitting, you are creating a pressure onto the table with the force what you are applying. Similar to that, radiation is also having a pressure. Radiation pressure they can call. It is having a mechanical effect. Radiation thought to be electromagnetic radiation thought to be dual nature, both particle nature as well as wave nature of that kind. Theory of light pressure, light means it is don't take it as a heavy and light. It is electromagnetic light of pressure were given by two great scientists, Maxwell and Albert Einstein. Clark Clark Maxwell worked in 1873 and Einstein in 1917, around that. Think actually how that theory evolved from 4 centuries actually. Whatever we achieved so far in technology, whatever we achieved in science is not the outcome of one person or a group of a lab or a group of scientists. It is the contribution from all actually. Whatever the mobiles you are handling, whatever the vehicles you are running, whatever you are eating with things, microwave ovens, whatever you are enjoying actually for your comfort in life is mainly because of the contribution from scientific throughout the world. Einstein was a great scientist. Albert Einstein only showed that the absorption and emission of the photons by atoms. If the atoms absorb the energy, certainly with the absorb the energy means they absorb and go to the excited state. And while during emission, they will emit the photon. The emission means that is while de-excitation, they will emit the photons. They modify the atoms and the linear momentum, or you can call it as the momentum of atoms to a time. The first process in which the photon momentum played an important role was Rampton effect. Rampton effect you might have studied earlier in your graduation in such a way. For any static or an isolated dead atom, if a photon comes and hits, certainly atom will go with the recoil energy and the release of the photons. The scattering of the X-rays against the electrons, for example, means electron is said to be a stationary particle and X-rays comes and hits and lead to the mechanical properties of the light, or we can also call the light pressure related. This led to the what we can call this is the last benchmark. The first proposal to the cool the coal neutral atoms in counter propagating laser beam was led by Ansch and Charlot in 1975. If you are not remembering the name of the scientist and the year, don't worry. You reproduce or you try to explain the concept. At the same time, a similar proposal was put forward by the Winland and the Dermite to be used for ions in an ion traps. Ions can be trapped, atoms can be trapped of that kind. But Hanshaw and Shallow have cooled the neutral atoms in pairs of counter-propagating laser beams, which were detuned slightly below a resonance transition of the atom. Since Doppler effect will tend to tune atoms moving towards one of laser beams into the resonance, these atoms will systematically be slowed down by the absorption of photons coming from the same direction and having the energy below the resonance. Therefore, since the emission occurrence in random directions, it only leads to a small isotropic velocity distribution. Therefore, the atoms moving towards the laser will cool down, will lose the energy, will lose the velocity, and effectively cool down. This is the technique how they achieve. Other atoms with velocity components towards the other lasers will cool in the same manner. Therefore, with a gas of ideal two-level atoms, one can easily calculate the limiting temperature, the so-called Doppler limit they can call, which for the resonance transition in sodium would leads to about 0.24 million Kelvin. Millikelvin, sorry, not million, millikelvin, a lower temperature. This is the experiment what they have done actually. Simple. Looks like that. Here you can see this should be a mirror between those two. It was cooled with the liquid nitrogen to the extent of that 0.24 million Kelvin. Okay. And this is the PMT tube, photomultiplier tube. This is one direction and another two. This is one, this is three, this is the one, this is the one, four, six. I told that no. Six side you put the laser beams to hint at. From one this because of this pressure, the atoms stay at the central point actually, at the central point. In 84, these two and co-workers at Bell Laboratories set up set out to realize the Doppler cooling proposed by the Hahn-Schumacher. What they used? They used a beam of sodium atoms, which first was slowed down by frequency shift or by pre-cooling to the laser. After this laser had been turned off, sodium atoms drifted into the six pairwise orthogonal counter propagating. See here, wherever. This is the one setup, this is the two setup, this is the three setup. This is three setup. This side there should be a mirror of that kind. In 85, group reported a cooling to a dilute vapor of the order of 10 to the power of 5 neutral sodium atoms. Right now, 10 to the power of 23 is our room temperature, 10 to the power of 5 neutral atoms with a volume of almost 0.2 centimeter cube, or you can call it as convert into the millimeter also, and they cooled to a temperature of about 0.2 millikelvin. Millikelvin. These atoms are not trapped, but fall slowly. It was not trapped actually. In fact, at that time, due to the gravitational field, cloud of cold atoms has a finite lifetime of about 0.1 second. They achieved only for about 0.1 second or 1/10 of a second. It remained there. The result of this temperature measurement was consistent with the theoretical Doppler limit for sodium to the extent of 0.4 millikelvin. Think of here 0.2 to 0.4 millikelvin. Further, optical molasses means keeping everything together to a great extent, experiment eventually led to an increase in density of the atoms to the 10 to the power of 9 per centimeter cube instead of about 10 to the power of 5 to 10 to the power of 9, and with a time of almost 1 second, almost 10 times more. The laser cooled neutral atom moving in an optical molasses to become really useful, one needed to trap. This trap had to be deeper than the magnetic trap, which was used by Philips in 1985. Even Philips bulbs, what you are calling, or Philips electronic goods, what you are calling, has come with his name actually. In 87, Richard and Chu, following these suggestions of the Talibot, developed an experiment on magneto-optical trap. They used magnetic field to trap the radiation and optical laser technique to trap the atoms. Three pair of counter-propagating laser beams. Here, this is the one, this is the beam. One, two, three, four, five, six. Okay, beams, but not with circular polarization and in conjunction with weak magnetic. Nowadays, the clocks have a precision of about 10 to the power of minus 14. In the sense, up to that of a second, up to that extent, 10 to the power of minus 14 of a second. While new design based on atomic fountains is predicted to have a precision which is far better than 100 times this 10 to the power of. You can go up to about 10 to the power. Here, I'm having a small video. Just watch it. It explains the phenomena. It reads just for a while. Are you able to see? Are you able to see? At least
Yes,
I need.
sir.
Okay, okay. Sorry. Sometimes it may not be in a proper way. What happened? Okay. You know, I will share this link also later. These are the two scientists. Same thing what I explained yesterday. I will share you. You can read later. The exact an atom, it goes with the resonance. During that time, it emits the photons, and this was achieved with the laser. Earlier, there was no laser. They worked with some other experiment. Two scientists came. This is the Hansch and Shallow. See, this is the one. 1, 2, 3, 4, 5, 6. You just confine. This the laser beams. It gets trapped. It works with the Doppler effect as it moves outward. The energy gets excited. See, this is the molasses they can call. This is the molasses call. As you come down with the temperature, this is the Doppler cooling limit they can call. I'm running out of the time. Just I'm thank you. See, this is the states. These states are not allowed. This will happen in normal case. Like that. How it happens? Assume that if you are exciting here, from here it goes to this by the absorption of the photons, means it go to the excited state. But while de-excitation will not jump here, it will jump straight away to the bottom. And this energy is sufficient to go for up. This is the effect called siphon effect, they can call. Boulders to the top of the mountain on similar way. This how much energy it can get. What they do? This is the waves. If you keep them the magnetic field like that, clockwise and anti-clockwise, here it will be trapped. This is the laser beam, which where the that is trapping the atoms, the transfer of the energy. Immediately zero field will happen. It retains the atoms at that point. Sorry, here I will take you a little bit. See that this effect from excited state to the de-excited state, it is coming down, down, down. Yeah, got resonance. This concept they captured. And rest of the part is the fine case. As a result, in the magnetic field forces, slow atoms will be trapped. Laser cooling has got a good effect of that kind. See that if they're aligned, these atoms will be pushed to the external field. See that, this is the center of the trap, and it will be trapped. But to do that, we need the low temperature. See that? It leads with the Bose-Einstein condensation or Bose-Einstein condensate. Okay. This I will explain. I'll take a break for about 10 minutes to store this video. We'll come back. Uh, uh, okay. I'll stop sharing here. And I'll stop.